Hello, y'all. Welcome to lesson 64 of my DP chemistry curriculum. This is section structure 3.1.10 HL section. This is going over transition element complexes are colored due to the absorption of light when an electron is promoted between the orbitals and the split d sublevels. The color absorbed is complementary to the color observed. We'll apply the color wheel to deduce wavelengths and frequencies of light absorbed and or observed. So this is what we're going to work on today. You'll make sure you need to know the color wheel equation, the color wheel as well as the equation C equals lambda times frequency, which are both in the data booklet, so you need to be able to use it. You do not need to know the different splitting patterns and their relation to coordination number, so we're not going to talk about that. So let's go over colored complexes. First off, this happens when we're often dealing with transition metals. We already talked about how transition elements make colored solutions, often colored solutions. So the big question is why? Why is copper blue or cobalt orangey red? So why do these solutions have color? Well, the first thing we need to remember is from an earlier section when we talked about complex ions, transition metals, transition metals will often form complex ions. And this is through So this is through the coordination bonds with ligands. So we talked about this when we talked about different types of bonds and coordination bonds, where transition metals will often bond to a ligand such as like H2O, OH minus, ammonia, NH3. These are all different ligands that can occur with a complex ion. Now, it does form the coordination bonds because these ligands will donate both their electrons to the ion. And the big thing here is that when this happens, electrons from ligands will be at varying, I think it's y, varying distances from electrons in d orbitals of the transition element. So this is where we have to start looking at the shape of the d orbital. The other thing we're going to do before we go into that is that we have to know that we're going to have a variance in shape and orientation of d orbitals in an octahedral complex. So this is bringing back electron domain geometry and molecular geometry. So these transition metal ions or things with d levels can form octahedrals, and they do this with the ligands. So we might see this in something like chromium hexahydrate. So this would be 3 plus, and it would make an octahedral shape. So let's take a look at those actual d orbitals. Now, you don't have to memorize the shape of these d orbitals, but they look like this. So you'll notice we have our dxy, dx squared, dyz, dz squared, and dx squared, dy squared. And these are the 5 orbitals, the 5d orbitals and their shapes. A couple things you'll notice is we have a coordinate plane here, or actually down here, z, y, x. And you'll notice that dxy isn't fully on the coordinate plane. They come out between the x and y. That is why it's called zxy, because these orbitals fit between those axes. Dx squared is across the x, both top and bottom, both backwards and forwards. Dzy is between dz and dy. But dz squared is directly up and down, and dx squared y squared is on the x squared and y squared axis. The beauty of these two right here is they also match where the ligands end up. So this is a secret to colored complexes. Specifically, our dx squared, dy squared, and dz squared orbitals are in the same axes as the ligands in an octahedral complex. So what this means is that these electrons are closer to electrons in ligands. They're quite literally and physically closer to those electrons, and the electrons will repel each other. So d orbitals, specifically these two d orbitals, will feel a repulsion from the ligand, and therefore have a higher energy. So because these d orbitals, so normally we have our 3d, and they are all of equivalent energy. But this might be in maybe Cr3+, so the ion. However, in the complex of CrH2O6, 3+, where we have 6 ligands creating the octahedral complex, we will instead have our 3d orbital oriented like this. The d orbital splits. Here's our dx squared, dy squared, and dz squared. And these orbitals will have higher energy. So this is the key point of this. The ligands split the energy of the d orbitals. This is called d orbital splitting. Quite aptly named. And the key thing here is that we now have a change in energy. Change in energy. Therefore, electrons in lower orbitals can be promoted. Furthermore, the change in energy of d-level splitting is equivalent to energy of visible light. That means light could theoretically interact with this electron and promote it to a higher energy level. So these can now, instead of just letting light through, absorb it. So our key aspect here is going to be visible light will be able to, I don't like that green. So visible light can promote these electrons. All right. Now, when we're dealing with energy and we're dealing with light, we have a couple equations we need to know. I'm going to change colors. Energy is equal to Planck's constant times the frequency of light, and the speed of light is equal to the frequency times the wavelength of light. Therefore, we can combine these into the energy is equivalent to Planck's constant times the speed of light divided by the wavelength of light. And this can now tell us specifically the wavelength of light, specifically visible light, correlates to the change in energy of split d orbitals. All right, so this is where this all comes together. We have a color wheel that we can use. And this color wheel is in section 15 of your DP chemistry data booklet. And what basically we see is that the color absorbed appears to us in solution as the complementary color, basically the opposite on the wheel. So for example, if we absorb blue light, the solution will look orange. Vice versa, if we absorb orange light, the solution will look blue. And we can just kind of color over violet with an actual violet instead of a dark blue. So that's kind of how this color wheel works. We have ranges of wavelength. So anything orange, anything that appears orange is actually absorbing light between 424 and 491 nanometers. So if it's absorbing about 450 nanometer wavelength, the solution will look orange. If it's absorbing about 525 nanometer wavelength, the solution will appear red. If it's absorbing 410, it will appear yellow, etc. So let's go ahead and actually try and bring this all together and do a problem. So for example, a violet solution absorbs light at a wavelength of 580 nanometers. Let's just double check that that makes sense. It's absorbing 580, it's in the yellow range, therefore it would appear violet. That is correct to us. All right, so the problem has two parts. One, what is the frequency of light absorbed? And two, what is the energy of the D-level split? Or the change in energy of the split. So we'll solve these in two ways. You can pause it and try and do it on your own. Otherwise, I'm going to start solving right now. So for frequency, I just do C equals frequency times wavelength. Therefore, we can rearrange that to frequency equals C over wavelength, which is 3.0 times 10 to the 8th meters second inverse divided by 580 times 10 to the minus 9th meters. And the reason I had to do this conversion is because nanometers is 10 to the minus 9th, so I had to convert nanometers to meters. When I plug this into my calculator, I get an answer of about 5.17 times 10 to the 14th seconds inverse, which is our unit for frequency. You may remember that from when we did light forever ago. For energy, I'm just going to do delta E, or actually we can just delete the change, just energy is equal to HF, Planck's constant times the frequency. We found the frequency and Planck's constant in your data booklet as 6.63 times 10 to the minus 34th joules seconds. We'll multiply that by 5.17 times 10 to the 14th seconds inverse. Our seconds inverse will cancel with our seconds, and we will get a total energy of 3.34 times 10 to the minus 19th joules. All right, this is how we solve it. You can also go backwards. If you're given joules, you can work your way to frequency and work your way to wavelength, which works your way back to color. So you can go both ways, and the DP will absolutely have you do that. The last thing before we end this is how do we quantify transition metals in solutions? So when you put them in solution, often the higher the concentration, we can guess what's going to happen to the color. And we know that the higher the concentration, the deeper the color. It'll become darker. Therefore, it would theoretically absorb more light. If we have more D levels to split, more atoms that have done that splitting, we will all in all absorb more light into those D orbitals. So we can therefore use a colorimeter, which measures absorbance. to quantify amounts. Now, the thing is, to do this, we need what's called a calibration curve, which, funnily enough, is not a curve. So for a calibration curve, we measure known values, known amounts of metal, or known amounts of concentration, metal concentration. And we plot them. So we could look at absorbance and concentration. This might be 0.1 mole decimeter cubed inverse, 0.2, 0.3, and our absorbance might create a graph that looks like this. And this would be our calibration curve. Then we take our unknown. So this could be our unknown amount. And that's the absorbance value we get. And that will lead us to a now found concentration. So whenever we're looking for transition metal complexes in a solution, we can often use this method. This is a tried and true practice method, and it just uses a little bit of algebra. You can often find the equation of the line using any line, point, slope, form, whatever, to get that equation, and then plug your value in to find your concentration. So I hope this helps you understand transition metal complexes a little bit better, and have a great day.